All right, let's go ahead and get started. So we're going to continue our discussion of deep learning. So today's going to be the last lecture on supervised learning, and the next lecture, I guess based on the poll that we took, is going to be on reinforcement learning. So in the previous lecture, we continued our discussion of multi-layer neural networks, and then we used this TensorFlow playground to basically see the kinds of rich nonlinear functions that multi-layer networks allow us to efficiently parameterize. And then we talked about how we can train multi-layer networks using stochastic gradient descent. And then we looked at overfitting. So what happens when you just minimize your training loss? You can do that pretty well, but potentially at the cost of not doing so well on the thing that we actually care about, which is the test loss. And then I discussed two kind of classes of approaches for dealing with this problem of overfitting. So we talked about regularization in the previous lecture, where you augment your training loss with an additional loss, so a regularizer, which sort of encodes Occam's razor. So you try to find functions that are simple in some sense, while also minimizing your training loss. And I mentioned that, I guess in this lecture, we're going to talk about a slightly different approach, which is to be more clever about the architecture, the neural network architecture that we pick, such that it has fewer parameters. And that's another kind of structure, another kind of simplicity that potentially overcomes this challenge of overfitting. So I guess this was the multi-layer kind of neural network architecture we were looking at. So you have some input, which is a vector, so you can think of it as an image. And then we have a bunch of these intermediate representations. So at each layer, at each level of processing, we apply this kind of canonical form of a function, sigma of wx plus b. W is a weight matrix, b is a bias term, and h is the hidden kind of representation that we get. And then we do this a bunch of times until we get to the output layer. So that's our predicted label. So I guess to see what one of the challenges with this is, so imagine that you have an image corresponding to your x, so that's the input, and imagine that it's a RGB image of pretty low resolution. So here I'm assuming it's 200 by 200, right, which is like really, really low resolution. So the crazy fly cameras are much higher, so it's like 640 by 480. But even with this low resolution, the input dimension is 120,000, so 200 times 200 times 3. So that's the dimensionality of x. The weight matrix, W1, for the first hidden layer is going to have dimensions D1 by 120,000, where D1 is the dimension of the first kind of hidden representation. And we're probably going to want many layers, right? So the total number of parameters that you end up with when you parameterize multi-layer neural networks in the way that we've done so far is really, really large. If you have images that are larger size, or if you have like neural networks that are of a larger depth, or if D1 is even kind of anything reasonable, even if D1 is 100, you're already at like a million parameters, or I guess 1,000, you're already at a million parameters. So the kinds of neural networks we've discussed so far are called fully connected layers. So fully connected because each neuron, so each dimension of each hidden representation potentially depends on all the dimensions of the previous layer. So if you think about the arrows in this picture corresponding to dependencies, so what does each dimension of a hidden representation, each neuron depend on? Everything kind of depends on everything as long as you're going kind of left to right, input to output. What we're going to talk about today are convolutional neural networks. And the motivation for CNNs, convolutional neural networks, comes from the fact that these kind of fully connected networks that we've dealt with so far don't really exploit the structure of the image. So if you're looking at computer vision applications in particular, and if X is an image, we're kind of just flattening it, right? So we're taking X and we're just thinking of it as belonging to some vector space. So we're thinking of it as some large vector, and we're getting rid of the kind of spatial, like two-dimensional nature of the image. And CNNs, convolutional neural networks, take advantage of the fact that the input is not just some arbitrary vector, but the input is really an image. And they preserve the kind of spatial structure of images, as I'll discuss in a couple of minutes. But yeah, I guess this is the kind of picture I want you to have in your mind. So you have an image, which you can think of it as kind of a volume, where the depth dimension is 3 if you have a RGB image, and it's just 1 if you have a grayscale image. And the width and height are, I guess, what you would expect. Like that's the width and height of the image. And then CNNs are going to process these volumes. So you have an input volume, you process that into different representations until somehow you get to the predicted label. Okay, and I guess I should mention that a lot of the visualizations here are from this course at Sanford CS231. It's a really nice resource. And if you're interested in learning more about CNNs and other related concepts, definitely suggest checking it out. Okay, so again, just at a conceptual level, we'll get into the details in just a bit. But there's basically 2 kind of major differences that convolutional neural networks have as compared to fully connected neural networks. The first difference, like I said, is that we're not just treating X as some arbitrary vector. We're going to think of it as a bunch of neurons that are arranged in 3 dimensions. So we're going to think of it as a tensor. And then the second kind of really major difference is that neurons in a given layer, so basically each dimension, so when I say neuron again, I mean each dimension of a hidden kind of representation only depends on a small number of previous dimensions in the previous layer. So I'll get into the details again in just a bit. But yeah, I guess those are the 2 main distinctions. With the fully connected layer, each dimension of a hidden representation depends on all the other dimensions of the previous layer. With CNNs, that dependence is going to be much more sparse. Okay, so this is the kind of basic operation that happens in a convolutional neural network. So we're going to start with some input volume. So in this case, I'm going to work with 32 by 32 images, and these are RGB images. So you can think of this as a tensor, so a multi-dimensional array with dimensions 32, 32, 3. And then each layer in a convolutional neural network is going to transform a volume, transform a multi-dimensional array, a tensor, into some other kind of 3-dimensional volume. And then we're going to keep doing this, like I said, until we get to the output dimension. So I guess I want to make sure that this idea is clear, that we're not just thinking of the input as belonging to some, I guess, 32 times 32 times 3 dimensional vector space. We're thinking of it as a 3D volume, so we're thinking of it as a multi-dimensional array. And so you can kind of index into the input with 3 indices like I, J, and K. So I maybe corresponds to the X dimension, like the width. J corresponds to the Y dimension, the height, and then K corresponds to RGB, like which color channel you're looking at. So I guess any questions on that representation? Okay. All right, so the main operation that does this like transformation from 3D volumes to 3D volumes is what's known as a convolution, a convolutional layer. So I'll describe that operation here, and then we'll talk about how that gets composed when we have like multiple layers. So the convolution operation operates on like this 3D volume, so a 32 by 32 by 3 image in this case. And what we're going to do is take a kernel, a filter. In this case, this kernel is 5 by 5 by 3, so it's another kind of smaller volume of elements, 5 by 5 by 3. And we're going to convolve this kernel, this filter, with the image. So what that means is that we're going to take this filter, we're going to place it at a certain location in the image. We're going to calculate the dot product between the filter weights, so the elements of the filter, and the elements of the input in the region that we're looking at. And then we're going to do this at all the different locations in the image. So that's the kind of high-level picture. I'll give a visualization in just a second. And I guess convolutions are something we've seen previously. So when we were looking at edge detection, so back in the very first lecture on computer vision, one of the first ideas we had for how to do edge detection was using convolutions. So we said if I have a one-dimensional image, a grayscale image in this case, to find edges, what I can do is apply this kernel, so -1, 1, 0, to the image. So convolve this kernel with my one-dimensional image. So if I kind of take the dot product in the very first location, I get, let's say, -1 times 0. So I pad the image on both sides with zeros. So it's -1 times 0, 1 times 5, and 7 times 0. And I keep doing this. So it's 5 times -1, 7 times 1, 6 times 0. That's 2. And if I do it here, 7 times -1, 6 times 1, 41 times 0. So that's -1, and so on. And I do this at every location in the image. And I get a bunch of numbers at the end, right? So I started with a one-dimensional image, and I end up with a one-dimensional array as well. Question? Yeah. Yeah. So the 3 is RGB. Yeah. So if it's a grayscale image, then it'll be 32 by 32 by 1. Yep. Okay. So convolutions are, or I guess, I mean, we're going to apply convolutions in the same way as we did for the one-dimensional case, except now that instead of 1D arrays, we kind of have 3-dimensional arrays, multi-dimensional arrays with the dimensions being 32 by 32 by 3. So we take this, in this case, 5 by 5 by 3 kernel or filter. I guess those terms are used interchangeably, and we're going to do this convolution. So the way this works is we're going to take the 5 by 5 by 3 kernel and place it at a certain portion of the input space. So you kind of have two 5 by 5 by 3 arrays that are kind of overlapping with each other, and you just take the dot product and potentially you add a bias term. So we have these two 5 by 5 by 3 chunks. We're doing element-wise multiplications, and then we're just adding up all the element-wise products. And so you end up with a 75-dimensional kind of dot product, if you want to think about it that way. And then you add in maybe a scalar term, if you like. And then, so I guess maybe let me just pause here and make sure that this operation is clear. Any questions on like the dot product, what it means? Okay. And you do this at every location. So you take the kernel, this filter, and you slide it along the image. So every location of the image. So for every location, you get one number, right? That's the number that you get when you take the dot product. So at the end of this operation, what you end up with is a 28 by 28 by 1 array. So 28 by 28, so you're losing dimension in this case because we're not padding the image. So we're not making the image larger. We're just taking this 5 by 5 by 3 patch and placing it, I guess, wherever like the image like actually kind of exists. And so we lose some dimension. So we went from 32 by 32 to 28 by 28. And this thing is called activation map. So the thing that you get, the bunch of numbers that you get, the array that you get after you do this convolution operation. Okay, and then you can do this with a different filter. So if you pick a particular kernel, so a particular 5 by 5 by 3 array to do the convolution with, you'll get one particular activation map. If you take a different 5 by 5 by 3 array and do the convolution, you're going to get a different 28 by 1 activation map. And then you can do this kind of multiple times. So let's say you have 6 different filters, 6 different kernels that you do convolutions with. Each one gives you a 28 by 28 by 1 array. And if you have 6 of them, you have 6 times 28, or 28 by 28 by 6, and that's kind of what's visualized over here. So I guess this is the main operation. So I mentioned with convolutional neural networks, you start off with some block, like some multidimensional array, 32 by 32 by 3, and then you process it to get another block, another like multidimensional array, in this case 28 by 28 by 6. So I guess we can do this again. So maybe just as a question, so if we think of this as our intermediate representation, like our hidden representation, 28 by 28 by 6, how would you do a convolution again to get some other multidimensional array like after this? So let's say I wanted a 24 by 24 by 3 block after this. What is the operation, convolution operation, that I would need to do? Go ahead.
3, 5 by 5 by 6.
Yes, exactly. Yeah, so 5 by 5 by 6, if you take that as your kernel, and then you convolve that with this, so with 28 by 28 by 6, so the 6 needs to match, right? So the 5 by 5 by 6 has to match the 6 needs to match the kind of last dimension of this array. And then we're going to lose dimension again. So we went from 32 to 28. We can go from 28 to 24 if we look at a 5 by 5 by 6 patch. I guess if you want to maintain the dimension, then you can pad. So you can pretend like the image is actually larger than it really is by doing like 0 padding, for instance, or just extend the image with values that are on the boundary. And then you can keep doing this, right? So you can do one of these convolutional layers, so transform the input volume 32 by 32 by 3 into 28 by 28 by 6. In this case, I guess I'm doing 24 by 10, and so on, until you get to the output layer. And to make so I guess one important thing to maybe point out is that the convolutional operation is linear, right? So we're like just taking a dot product. So to end up with functions that are nonlinear, we need some activation map, like we need some nonlinearity. So the way convolutional networks are structured is that you do one of these convolutional operations, you apply these convolutional layers, and then you take an activation function. So the activation part is identical to what we discussed previously, so it's an element-wise nonlinearity. So let's say you're working with a sigmoid function. You take each element of this 28 by 28 by 6 array, and you pass each element through a nonlinear function, so you end up with another 28 by 28 by 6 array. And then you do another convolution, another nonlinearity, another convolution, another nonlinearity, and so on. So that's basically the computation, the sequence of computations that happens to go from input to output. And because we have these nonlinearities, convolutional networks are able to represent nonlinear functions, similar to how we were able to represent nonlinear functions with fully connected layers, like multi-layer perceptrons. So I guess any questions on these operations? All right. So I guess so I described what a CNN does, but why are we doing this? Like, why are convolutional neural networks a good idea? There's basically two main reasons. The first one is that we have significantly fewer parameters, right? So with a fully connected layer, we I guess as I mentioned a few slides ago, we potentially have a really large number of parameters, like the weight matrices, the bias vectors that we're trying to learn. With a convolutional network, we've significantly reduced the number of parameters that we're learning. So the thing that we're going to learn are the like filters, the kernels with which we do the convolutions. So each convolutional layer has number of parameters equal to the number of elements of the filter. So the filter, the first filter we did was 5 by 5 by 3 by, let's say, like 6, that's only like 450 parameters. So sorry, each kernel was 5 by 5 by 3, and I said we have 6 of them. So that's where the times 6 at the end comes from. That's only 450 parameters, as compared to, if we go back to the slide over here. So if we were doing things in the kind of with fully connected layers, we had 120,000 times like D1 like parameters, right? So that's significantly more parameters than what we have with a convolutional network. So the only thing that we're learning, maybe let me go back here. The only thing that we're learning are the weights over here, like the elements of this filter. And if we have multiple filters, then we're learning like the parameters corresponding to all of them. But that's still a tiny number as compared to what you get with a fully connected layer. Okay, so that's one reason. So we're significantly reducing the number of parameters that we're learning. The other reason is that convolutional networks are exploiting spatial invariants. So if you're doing object detection, let's say, so if you're trying to determine whether there's a cat in the image or not, then like these visual features are kind of spatially invariant. So if you have a cat in this part of the image, that's kind of the same as having a cat in this part of the image. And similarly with other features, so like lower level features like edges or corners. So an edge in one part of the image is kind of the same as an edge in a different part of the image. And that's, I guess, one of the justifications for convolutions. So you can think of these convolution operations as doing some kind of feature detection. Like we're saying, is there an edge? So that's what we did with the one-dimensional array, right? Like the 3 by 1 convolution that we did. These are like more sophisticated versions of that. Like we're asking, is there a particular feature here? Is there a particular feature here? Is there a particular feature here? And we're using the same feature detectors, like the same kernel in every portion of the image. And this makes sense in vision because of the spatial invariance. Question?
How do you choose the size of the filter?
Yeah, so the size of the filter, it's kind of, there's some like rules of thumb. Like you usually, like 5 by 5 by 3 or something like that is usually like what you would pick. So part of it depends on the scale of features that you're trying to extract. So typically, I guess this is kind of showing like visualizations of the features. So typically what happens is that the features that you're looking for at the beginning are kind of low-level features, like things like edges and corners and so on. And then as you go deeper into the network, you start getting features that are more like complicated, and then at the end you get like more and more kind of complicated features. There's no kind of theory really to tell you like what size of the kernels to pick, but the intuition is that if you pick something that's too small, then you're focusing on like tiny portions of the image and asking, is there some feature here, is there some feature here, and so on. And so you're not getting that much information if you're just zooming in on a very tiny portion of the image. If you make the kernel size too large, then you're kind of looking at the entire image almost, or a significant portion of the image. And there's a bunch of stuff happening inside, right, that you're missing out on. So there might be a bunch of edges or a bunch of corners in a large portion of the image, and so you're not necessarily sensitive to changes in those. So yeah, I guess something like 5 by 5 or maybe 7 by 7 is typically pretty good for computer vision applications. Yeah. Good. Other questions? Good. Yeah. Exactly. Yeah. So what this is visualizing is basically what features of the image is a particular layer sensitive to. So that's kind of what's being visualized here. So lower level like features are sensitive to initial like representations, like kind of in the beginning of the network, are sensitive to low-level features like corners or edges, and then as you go deeper in the network, they get like more sensitive to more like complex like patterns. And these are for like trained networks, right? So I think this is for a convolutional neural network that's trained on ImageNet. These are the features that end up being learned like after you do stochastic gradient descent. Yep. Okay. I guess other questions on convolutions? Okay, so convolutional networks, I guess, have been around for a long time. So early CNNs were proposed in the 1990s by Jan LeCun and his collaborators. There was a bit of a kind of deep learning winter that lasted all the way to about 2012, or maybe a little bit earlier, 2010 or so. And I mentioned this before, so I guess the big thing that happened in 2012 was AlexNet. So this was work from Jeff Hinton's group, where they used convolutional neural networks to basically beat the state-of-the-art for the ImageNet image recognition competition by a massive margin, and that got people really excited about deep learning and convolutional nets. And of course, I guess things have gone kind of crazy since then in the last 10 years. And there have been many variants, right? So I guess what I described is the most kind of basic version, the vanilla version of a convolutional neural network. There's a lot of bells and whistles that you can add that really make a big difference, or can make a big difference in practice. And these things kind of some of them tend to stick around, some of them are really popular for like a year or two, and then people move on to other things. So like VGG networks, like, were really popular in 2014. There were other architectures, Google Nets and Inception, that were popular in 2014. Residual networks, popular in 2015. Those are like still around actually, and there's lots and lots of variants. I'll say a bit more how to maybe choose the architecture, but go ahead. There's no great methodology. It's like people like some researcher has some intuition for like what structure, like what bias in the architecture, what structure in the architecture might improve performance. They try it out. If it works well, they write a paper, and if it works even better, then other people use it, and so on. There's no like deep like theory. It's like very empirical. But I guess there are a few things. Actually, maybe I can add a bit more to that. So there are a few sort of things that people try to do with architectures. So one thing is, like, can you encode inductive biases? So by that I mean, can you somehow exploit the structure that's inherent in your data? So the nice thing about CNNs is that they're exploiting spatial invariants. Like I said, like some object in one portion of the image or some feature is the same as in some other portion of the image. So things are spatially invariant. If you have kind of those kinds of intuitions for like what structure might be inherent in your data, and if you find a way to bake that into the architecture, that can make a big difference in practice. The other big thing is, can you somehow just make the learning process, like the stochastic gradient descent, like the optimization process, more efficient somehow? Like the computations that go in there, can you make that more efficient? And that allows you to soak up lots and lots of data. So if you have some architecture that has the kind of right structure while also being able to be optimized pretty efficiently, that's a win. I guess that's some maybe rough intuition for what people are trying to do when they come up with new architectures. I guess one thing that people have found generally is that increasing the size of the networks, increasing the depth of the network, for instance, can be massively effective. Increasing the depth of the network can make the optimization with stochastic gradient descent harder. And so that's one kind of direction, like especially with the residual networks, ResNets. people found a way to have like pretty deep networks, so many layers of processing, while at the same time making the optimization with stochastic gradient descent not kind of super prone to getting stuck in local minima. And yeah, state-of-the-art architectures can have many, many layers. So I put greater than 15 layers, but that's kind of arbitrary. These numbers like keep changing or keep increasing year on year. And this is showing the top one accuracy for image classification on ImageNet compared to the number of operations. So you can think of the x-axis as kind of corresponding to the number of parameters roughly in your neural network, and you find typically that as you increase the number of operations, as you increase the complexity of the network, while keeping some of the basic architecture, like with convolutions, constant, that gives you better and better performance. So yeah, I guess somehow training larger networks on more data gives you better performance. So I guess one question is like, what architecture should you choose in practice? I mentioned there's lots of variants of convolutional networks or even other architectures. So one rule of thumb is just see what is currently state of the art for ImageNet. I guess if you care about computer vision or if you care about something else, natural language processing, for instance, then see there's like kind of well-established like benchmarks at this point. See what is doing really well, what's the state of the art today, and that gives you a sense for what architecture you might want to use. Yeah, and in practice you'll find that this gets you most of the way, 80–90% of the way, maybe all the way, but then maybe there's a little bit of kind of extra performance that you can squeeze out by being even more clever, by exploiting more structure that's specific to the learning problem that you're interested in. So if you have some domain knowledge, then you can try to bake that in somehow. Nowadays, there's actually been kind of an interesting convergence towards transformer architectures. So I won't have time to go into them. But these were developed in the context of natural language processing. So I guess if you've heard of like GPT, GPT-3, and many other large language models, transformers are kind of at the heart of those. And they're becoming more and more popular for other kind of non-language based applications as well. I think for computer vision, it's not the case that I guess transformers are necessarily state of the art. There's a bit of a kind of battle. I guess someone comes up with a transformer architecture for vision, and then someone says, oh, actually convolutions are still useful, and then there's no consensus. But I think what's interesting is that there is a bit of a convergence. Like people are like before. I guess on this slide I had a whole bunch of things before 2017. Like every year there'd be like 2 or 3 things that people were excited about. Since 2017, it seems like there's like the deep learning, I guess, community as a whole is moving more and more towards transformers. I think for vision, convolutions still make sense because they're exploiting like the spatial invariants, but combined with like these transformer architectures, like seems to give really good performance. Question?
At a high level, how
Yeah.
is the transformer being applied to ImageNet? From what I understand,
Yeah.
transformers are for sequential.
Yeah. So transformers are for data that are inherently sequential, like language. So if you have a sentence, there's a bunch of letters or a bunch of words, and transformers do that. So the way transformers get applied to non-sequential data, like an image, so an image is not inherently sequential, is by, they call it like tokenizing. So you basically treat the image as a sequence. You can like chunk up the image into different parts. You can think of that as a kind of sentence, if you like, or I mean just a sequence, and then you pass that to the transformer. It seems like a very kind of weird thing to do. It seems a bit hacky, right? That you're taking this thing that's not necessarily a sequence and like basically treating it as a sequence. But yeah, somehow surprisingly, that sort of thing seems to work pretty well. Yeah. So yeah, I guess if you're interested, there's a paper. So vision transformers, like VIT. That's the essentially state of the art, as far as I know anyway, for using transformers for vision, and they're at least competitive with convolutional neural networks for vision, and for language tasks, they're like by far, like there's complete consensus right now that transformers are what you want to use for language tasks. If you're interested in transformers, actually the original paper from 2017, this was from Google, Attention is All You Need, is actually a really good resource. So it's often the case that the original paper is not super readable and is maybe not the best resource. That's not the case here. This paper is really nicely written, and if you're interested, I would maybe start here. And there's a bunch of like blog posts as well that do a good job of explaining transformers. Okay, I guess the other thing that you might want to consider is to use pre-trained networks. So we kind of did this for the lab, the most recent lab, with the object detection. So if you're looking at computer vision tasks, you could take a neural network that's been trained, let's say, on the ImageNet dataset to do image classification. And then maybe you are interested in a different task, like maybe you don't care about image classification, maybe you care about something else. You can still reuse most or like parts of the network that was trained to do image classification. The idea is that you take the network that was trained to do image classification and you keep the first few layers, or like most of the layers, and you basically retrain just the last one or two layers, maybe even one layer, for your particular task or for your particular data set. So this is called fine-tuning. And yeah, I guess the intuition is that features that are useful for object recognition, which is what this original network was trained for with ImageNet, are also useful for your particular application. So being able to detect edges or corners or other kind of more complex visual features it's kind of like generally useful, right? It's not just useful for object recognition, but many other computer vision tasks also benefit from being able to detect those visual features. Okay, so I guess to make all of this work, there's a bunch of different software libraries. So I've listed just 5 of maybe the most popular ones here: PyTorch, TensorFlow, JAX, Caffe, and Keras. These things do a lot. These software libraries do a lot of different things, and I guess the availability of really mature software, I think, has led to a lot of the progress that we've seen in deep learning over the last few years. So these packages, these toolboxes, allow you to pretty easily specify different architectures. If you want to play around with different variants of convolutional neural networks, they allow you to build those variants pretty easily. They allow you to load existing architectures. So you can just say, build me a transformer or build me a convolutional neural network that has kind of these number of layers and these like dimensions for the hidden representations, and they'll just like do that for you. You can choose different optimization schemes and different parameters within the optimization schemes. For example, the learning rate, or different variants of stochastic gradient descent. I mentioned Adam in particular. That's the most popularly used one. There's a couple of other ones that people also use. You can load different data sets. You can say load like the MNIST data sets. That's the handwritten digits, or load ImageNet, or load kind of any number of other data sets that are freely available online. And I guess importantly, they also allow you to interface with GPUs and cloud computing resources in a kind of, so you basically don't have to worry about how the computations get spread across GPUs or across multiple like CPUs if you're working with a server. So I guess these software libraries handle that kind of multi-processing for you. So yeah, I guess CNNs are like I said, pretty much state-of-the-art for all or most computer vision tasks. So image classification, semantic segmentation, so looking at each pixel and saying, is it a road or a pedestrian or a bicycle or so on. Image captioning. Yeah, I guess image captioning is a bit different because there's a language component, and nowadays, like I mentioned, transformers are taking over there. pose estimation, which is important for robotics, and many, many other computer vision applications. So I guess what I want to do for the rest of the lecture, or for part of the lecture, is to talk about applications beyond computer vision. So far, we've been motivating almost everything with vision tasks. So we've thought about X, like our input, as corresponding to an image. But neural networks are not just for computer vision, but can be used for lots of other things as well. So I guess one of the most maybe direct applications of everything we've discussed so far is imitation learning. So let me play a video, and then I'll say a bit more about imitation learning. So this is a video from 1989.
Years ago, who would have thought that cellular phones would be as common as they are today? Well, we may be thinking the same thing someday about our next story. CMU's Robotics Institute is developing a car
Can you
that
hear
can
the
drive
audio?
itself, and it's already being tested on the road. Money editor Bill Flanagan went along for the ride.
Todd Yoakum is behind the wheel of this Army ambulance, but the CMU graduate student isn't driving. A computer is. The machine watches the road through a video camera perched above the windshield and steers the vehicle itself.
We've had it up to 70 miles an hour, and it's driven autonomously for over 90 miles straight without the human ever touching the wheel.
That's right. This robotic vehicle is driven to Erie and back on I-79. It's the result of 8 years of military research at CMU's Robotics Institute. Scientists here don't teach computers how to drive. Instead, they use a computer process called a neural network to create a machine that can learn to drive. Dean Pomerleau is the project director.
We don't tell it anything except steer like I do. Learn to steer the way I'm steering right now. Sometimes it keys off of the road edges. Sometimes it looks for the painted lane markings down the center of the road. So it varies, and it learns in different conditions what important features are on that road type.
At slow speeds, the NavLab can use a laser rangefinder to spot and avoid objects in the road. But to date, it's too nearsighted to do it at highway speeds.
It may be a while before you'll be able to buy a robotic car that can run on down to the convenience store on its own, but perhaps not so long for robotics technologies pioneered here at CMU to begin showing up in state-of-the-art cars and trucks.
The Robotics Institute recently received a more than $2 million grant from the U.S. Department of Transportation to find ways to use the military technology to improve highway safety. Chuck Thorpe's the principal investigator.
There are 13,000 people killed every year just by running off a road. Single vehicle accidents.
One potential lifesaver, a warning system that could sense when a vehicle is drifting off the road and awaken a sleeping driver. The Robotics Institute is well on its way to creating one. Bill Flanagan, KDKA-TV, Eyewitness News.
Yeah, I guess it's kind of interesting to see what things they were right about, what things they were wrong about. So the alert system, that's something we do have nowadays, right? That they were right about. I guess they were also kind of right when they said that, yeah, it might be a while until we see autonomous vehicles that just go down to the grocery store. We still don't have those. But yeah, I mean, what's interesting here is that they were using imitation learning. So basically, you have a human that shows the robot how to drive. So the human provides lots and lots of data of just driving around in different road conditions. And then essentially this is, you can think of this as an analog to image like recognition, right? So this is a supervised learning problem. So at every time step, the robot receives some image, some input, some sensor observation, and then we've told it what the kind of correct label is, what the correct action is, and then we have this data set of images or sequences of images and labels of like steering outputs, and then we can just fit a neural network to this data using the techniques that we've discussed in this course. So I guess imitation learning is really powerful and still being pretty heavily utilized for modern day autonomous vehicle system development. This is a video by Wave. I think it's a couple of years old now, but let me just play it. driving in the UK. That's why it's on the other side of the road. Yeah, so it's kind of interesting. I mean, it's all imitation. Like the only thing that the neural network is learning to do is imitate the human. And I guess they're saying that, I think over here, somewhere at the end over here, yeah, no hand-coded rules are specified. All behavior is learned from the data, which I think gets you some way, but I guess some of the rules we might want to bake in, right? Like stop at a red light. Seems like a good thing to bake in rather than to learn just by imitating human data. But yeah, I guess imitation learning gets you part of the way there. It's like pretty impressive, like what you can get with imitation learning. With I think not a lot of data, right? They were using I forget what it was exactly, like 30 hours of human driving data, which is not like a massive kind of investment in data. And if you have like more data, then you can get better performance. Question?
Since this is in Europe, like specifically the UK, I'm wondering like how do they can you use data from places like this to do driving in the US if it's on a different side of the road, like, or how can you parse like what's useful?
Yeah, so that is a major challenge, yeah, I mean, I guess with the other side of the road, you could probably like hand code some like transformation maybe. You can like pretend everything is like flipped or something like that, and then use the same neural network. But there's other things that are much more like subtle, right? Like the width of the roads, or like visual features that appear, or even like conventions. So even like different states within the US have like different like rules, right? I guess I think New York, yeah, turning right on a red traffic light, or whether you're supposed to like how you merge into like a roundabout or like stuff like that. There's a lot of like local conventions, and I think that's one of the reasons you see like autonomous vehicle companies like mostly focusing on a couple of cities, right? So Waymo started off in Chandler, Arizona. Did a bunch of kind of years of testing there and deployment there, and have recently kind of moved beyond to San Francisco, and I think to LA as well, if I remember correctly. I guess all cities that have kind of nice sunny weather for the most part. But like going to like from there to like New York City or to a different country is like pretty challenging, and not something I think that or something that's still a major like open like research challenge. Yep. Good. I guess other questions on this? Go ahead.
How do you combine like fixed rules with like the data that it just learns?
Yeah, it's tricky. I mean, you can go in kind of your code and add like if statements. So you could say like if you see a traffic light, red traffic light, stop. Else deploy imitation learning policy, something like that. But yeah, it's not super obvious, and I guess that's one of the appealing things of using imitation learning, or just pure learning without trying to hand code things, is you don't need to worry about how to like take in like rules and bake them in. But at the same time, yeah, it seems a little bit strange to learn everything, like things that you can hand specify, like really hard rules. You should probably like bake in. But I guess one of the lessons I think from learning has been that like you have to be careful about exactly what you bake in. So as an example, you might want to say never cross the like double yellow line, right in the middle of the road. But that's something that humans do like all the time. So if there's a car kind of parked in front of you, then if that was like truly a hard-coded rule, then your autonomous vehicle would just sit there and do nothing, right? And just like wait for the person to come back, whoever's like double parked and like take the car away. I guess what humans do is just wait for like the oncoming traffic to stop, cut across to the other lane a little bit and go back. So I think that the number of things that you want to hard code is probably relatively small, but some things like stopping at red traffic lights seems good to hard code. And like turning right on a red traffic light, like those kinds of things seem like they should be hard coded too.
So you would like take the traffic handbook or given like read it and say like these are all the rules that I'm going to hard code in there.
Yeah. Yeah, definitely not. So people, I guess, tried doing this in the earlier days of autonomous vehicles. So DARPA, like that's the defense agency that like funds a lot of this, or funded and funds a lot of this research, had some competitions, and I guess back in the day then, like 2005, 7 or so, there was much more like hand coding. So this was like like the modern like deep learning revolution. But yeah, I guess they found that the cars would just do silly things for the sake of following the rules exactly like 100% of the time. And so yeah, I guess humans like break like all the traffic laws, traffic rules, right? Like we break them like all the time, and I think for good reason, or I guess mostly for many times, often let's say for good reason, or not always for bad reasons. Good. Other questions? Okay, so I guess imitation learning is not just for autonomous vehicles. Here's just a 2-minute video showing imitation learning in the context of robotic manipulation.
Infants are born with the ability to imitate what other people do. Here, a 10-minute-old newborn sees another person stick their tongue out for the first time. In response, he sticks his own tongue out. Imitation allows humans to learn new behaviors rapidly. We would like our robots to be able to learn this way too. We've built a proof of concept system trained entirely in simulation. We teach the robot a new task by demonstrating how to assemble block towers in a particular way, which in this case is a single stack of 6 virtual blocks. Previously, the robot has seen other examples of manipulating blocks, but not this particular one. Our robot has now learned to perform the task, even though its movements have to be different from the ones in the demonstration.
Okay, so all right. So I guess this is kind of the end of our discussion, or almost the end of our discussion on supervised learning. So as I said, we'll talk about reinforcement learning and some deep reinforcement learning in the next lecture. Yeah, I guess given like the limited amount of time, I've only provided a very brief intro to deep learning. There's massive amounts of like work, massive numbers of people that are working in the area, and there's been a massive amount of impact already in the last 10 years in particular. So here's some resources if you're interested in diving further. So this deep learning textbook by Ian Goodfellow, Yahya Bengio, Aaron Corwell. This was written in 2016 or so. I guess these things tend to get kind of outdated pretty quickly, but some of the core ideas in that book are definitely still relevant. Deep learning with Python, that's another good one. There's a bunch of actual like code in there that might be worth checking out. A couple of courses at Princeton as well. So there's the computer vision course, theoretical foundations of deep learning that gets taught, I guess, every now and then, and foundations of RL also that's taught periodically in the ECE department. So I guess what I want to do just towards the end here is zoom out again. So we tried to do this a little bit with some of the other modules. So I want to zoom out and think about some of the broader implications of machine learning, deep learning, specifically as they apply to fairness. So we've adopted a kind of like technical perspective on learning so far, right? So we said we have this training data set, and we're going to just find some neural network weights, maybe by adding a regularizer, but essentially by minimizing the training loss, so just trying to fit our data, our training data, as well as possible. So I guess what could possibly go wrong? So there's lots of things, it turns out, that can go wrong. And one of the things that people have realized over the last maybe 6 or 7 years in particular has to do with fairness or unfairness that comes about from this kind of learning scheme. So one of the most maybe kind of well-known examples of this kind of algorithmic bias comes from recidivism. So recidivism is a legal term, so it's the risk of reoffending. So yeah, I guess if someone has committed a crime, what's the probability that they're going to commit another crime, and that sort of determines like bail amounts or whether someone gets bail and those kinds of things. So many states in the US use actually data-driven algorithms, so learning-based algorithms for predicting recidivism. And there's a software kind of in particular that received a lot of scrutiny called the Compass system, which basically has a data set of people and kind of labels associated with them, like whether they recidivated, like whether they reoffended. And you train something to make predictions and use those predictions on kind of new individuals. And I guess what people found is that these systems, these automated systems, can be significantly biased. And specifically, there were studies, I'll point to one in the next slide, showing that there's a significantly higher false positive rate for black defendants. There's some debate on the exact kind of rates of the false positive and false negative rates, but there's kind of general consensus that it's significantly different at least. So this is a study, I guess there's a fine print over there from 2018, studying this system, this Compass system, and they found that this kind of commercially developed software that uses learning is basically no more accurate at predicting recidivism than just some kind of random person, like untrained human, predicting recidivism. And I guess one of the implications of this is that there's a bias, in this case a racial bias, that humans have, like untrained humans have, and then also this Compass kind of system also like learns this bias. So the middle kind of block of bars is showing the kind of false positives. So a defendant is predicted to recidivate, but they do not. So false prediction of recidivism. And then the other side is kind of false negative. So a defendant is predicted to not recidivate, but they do in fact. And there's a kind of pretty significant difference based on race. So there's a higher false positive rate for black defendants and a higher false negative rate for white defendants, I guess, as they found in this study. And this problem is not just restricted to recidivism. There were other studies in the context of facial recognition. So this is Joy Bolomwini, who's is a researcher at the MIT Media Lab, and she and her group found that there's kind of racial biases for facial recognition algorithms that are also based on machine learning. And I guess part of this, there's different reasons for this and many other examples as well. And it's not just race, right? There's like other like demographic kind of features that can be discriminated against, and these show up in other examples. For example, automated systems for determining whether or not someone gets a loan, or examples in healthcare, and I guess almost any application where we're using learning to make predictions about people. And this bias, this unfairness can come from different sources. So a major source has to do with the training data. So if your training data itself is biased and you're just minimizing your training loss, then the thing that you learn is also going to be biased. There's potentially other sources of bias as well. So the learning algorithm or model evaluation and selection. So at the end, a human decides, like, should I deploy this model or not? And that can also introduce bias into the system. So I guess there's kind of consensus around fairness in the sense that we want our AI systems to be fair. I think most people agree on this, but it's not actually totally clear what exactly we mean by fairness. So at the end of the day, we somehow need to change our stochastic gradient descent algorithm, right, or something like our neural network architecture to ensure fairness. And to do that, we have to be mathematically precise about what we mean by fairness. There's two categories, two kinds of fairness that one could consider. So the first kind is what's known as group fairness. So this is the kind of fairness that I guess I've been motivating with the examples on the previous slide. So here you have some algorithm that takes in as input, so this is kind of our X, like an individual's data, and then you have some output, let's say a binary output, binary label, maybe prediction for whether this person will recidivate or not. So group fairness basically imposes statistical requirements about the treatment of different groups. So let's say treatment of different racial groups, but in general it could be any kind of demographic group, race or age or so on. So there's different possible definitions you could come up with for group fairness. So a pretty reasonable one is that across different groups, so let's say across different races or across different ages, you want the false positive rate to be equal, right? So false positive is if you make a positive prediction, but actually the label is negative. So incorrectly predict recidivism, for example. Another possible definition is that you want the false negative rate to be equal across your different groups. Yet another possibility is equal positive predictive value, PPV, across groups. So this is related to the false positive and false negative rates. So PPV is so among those who are predicted to recidivate, how many of them actually do. So it's the number of true positives divided by the number of total positive calls. I guess the details are not super important. What I want to convince you is that these three are all pretty reasonable definitions of fairness. The punchline is that there's this kind of neat theoretical result from relatively recently, about 6 years ago, that says that there's no classifier, so no algorithm, that can simultaneously ensure these three kinds of fairness unless the classifier is absolutely perfect, which is not possible. We're learning from some data. We're not going to be 100% accurate on all individuals. Or if the base rates of, let's say, recidivism are exactly equal across the group, which is across all the groups, which is also not realistic. So basically what this result is saying is that in practice, it's impossible to achieve these three kinds of fairness simultaneously. So I think this is a pretty counterintuitive result. It seems like all of these definitions, all three definitions, are pretty reasonable, but yeah, there's no way to achieve them simultaneously in practice. So basically what this means is that we need to choose, we need to commit to some notion of fairness, and we cannot have everything here. So that's one, I guess, kind of fairness, group fairness, so fairness across different demographic groups. There's a different kind of fairness, which is called individual fairness. And roughly what this means is that similar people are treated similarly. And to explain this, there's a really kind of funny and nice video, which I'm going to just play.
So the final experiment that I want to mention to you is our fairness study. And so this became a very famous study, and there's now many more, because after we did this about 10 years ago, it became very well known. And we did that originally with capuchin monkeys, and I'm going to show you the first experiment that we did. It has now been done with dogs, and with birds, and with chimpanzees. But with Sarah Brosnan, we started out with capuchin monkeys. So what we did is we put two capuchin monkeys side by side. Again, these animals, they live in a group. They know each other. We take them out of the group, put them in a test chamber. And there's a very simple task that they need to do. And if you give both of them cucumber for the task, the two monkeys side by side, they're perfectly willing to do this 25 times in a row. So cucumber, even though it's really only water in my opinion, but cucumber is perfectly fine for them. Now, if you give the partner grapes, the food preferences of my capuchin monkeys correspond exactly with the prices in the supermarket. And so if you give them grapes, that's a far better food, then you create inequity between them. So that's the experiment we did. Recently, we videotaped it with new monkeys who had never done the task, thinking that maybe they would have a stronger reaction, and that turned out to be right. The one on the left is the monkey who gets cucumber. The one on the right is the one who gets grapes. The one who gets cucumber, note that the first piece of cucumber is perfectly fine. The first piece she eats. Then she sees the other one getting grape, and you will see what happens. So she gives a rock to us, that's the task. And we give her a piece of cucumber, and she eats it. The other one needs to give a rock to us. And that's what she does. And she gets a grape. And she eats it. The other one sees that. She gives a rock to us now, gets again cucumber. She tests the rock now against the wall. She needs to give it to us. And she gets cucumber again. So this is basically the Wall Street protest that you see here.
Anyways, yeah, I guess so this is individual fairness. So similar individuals, I guess in this case similar monkeys, should be treated similarly. You can also mathematically formalize individual fairness similar to what we try to do with group fairness. And there's lots of different definitions. And there's a, I guess, tutorial from a Princeton professor who lays out 21 different definitions of fairness and their kind of associated politics. So the main, I guess, takeaways here are that there's lots of work, especially recently over the last five or 6 years, on mathematically defining what we mean by fairness, which we have to do if we ultimately want to bake these notions of fairness into our learning algorithms. There's a lot of interesting theoretical results which I think help us and force us to think about what we mean by fairness, not just for machine learning algorithms, but what do we mean by fairness even just for ourselves, like as humans or as societies. And yeah, I guess formal definitions, like I said, enable algorithms for enabling or ensuring fairness of our machine learning systems. If you're interested in learning more, there's a couple of resources. There's a really nice talk by Cynthia Dwork, who's one of the pioneers in this area of fairness, so the emerging theory of algorithmic fairness. Yeah, does a nice job of laying out the basic ideas and the basic kind of technical results. There's a Netflix, I guess, documentary called Coded Bias, which I highly recommend. It's really nice, overview of this issue. And there's also a book by Michael Kearns and Aaron Roth from UPenn called The Ethical Algorithms, if you want to dig deeper and see more examples of these, and some of the research is also I guess they're both professors at Penn, and so they talk about some of the technical approaches towards tackling this challenge as well. All right, so I guess any questions on this, on the fairness stuff or any of the other things? All right, I'll see you next time.